Okay, so first I want to make some important announcement about the future classes and also the midterm. So previously we would schedule the midterm this week, but then I feel like we're not ready. We just started and we have a lot of things to cover. So, and I think for you guys, you may need a longer learning curve to really have something to talk about, right? So that's why I would decide to, so in my previous announcement, I think I said I will do the midterm at the end of, and let me see, in week 6, I think that's the plan, because we also have some students who have some other arrangements. So that was the original plan, to do the midterm in week 6. But now the thing is that we have some changes about the teaching. So the university, if you have received the announcement, says that we will resume in-person teaching on January 31st. But on the other hand, I also received an email from the academic senate of the university saying that professors can do 2 more weeks of remote teaching. So I have received 2 emails about this. So because we have some students who will attend remotely, so then I think I will take that option and do 2 more weeks of remote teaching. I think another reason is that because I think we have this recording, right? So some of you may want to rewatch it. And I think the quality is much better when I do the recording this way than when I do the recording in the classroom and write on the board. So that will make the text harder to read. So that's another reason I think I will do 2 more weeks of remote teaching. So that will make our remote teaching until February the 9th. Okay, so that will be week 6. And then I want to do the midterm after that. So my tentative schedule is to schedule the midterm likely remotely. I think most likely remotely on February 14th, which will be the Monday of week 7. And then we will not have a class on that day. And so basically after the February the 9th, the Wednesday lecture, remote lecture, you will have some time to prepare for the Monday midterm before we go back to in-person in week 7. So I think that's the plan. Okay, so any questions here? So week 7 is when we meet up in person, then take a midterm. Yeah, but I think I will most likely do the midterm remotely just to accommodate some students. So therefore, if we do that, then our first in-person lecture will be February 16th, so the Wednesday. That's the current plan. And I will post what I just said to CCLE as a formal announcement, so nobody will miss the information. After 2 weeks, do we have hybrid option? Of course, that's a thing. So I think basically I already submitted a petition to undergraduate council because they said that beyond the week 6, if professors want to do remote teaching, we need to submit something. So I can tell you that I submit a petition to say that I think the quality of this recording is just better. So if they can allow us to do it, but if they don't, I will go back to the classroom, but I will still post the recording anyway and do the Zoom live streaming. So you can still attend it remotely. So yeah, so February 14th, the Valentine's Day. Okay, so any questions for this? Yeah.
I want to make sure the first class in person is February 16th, and
our midterm for now.
Yeah, and the midterm will be through the online, and when is gonna be the date for midterm?
So we said that February 14th, the Monday.
Okay.
And in the chat box. Yeah, in the chat box. So yeah, thank you for clarifying, everybody. And also I think, so we will just use so for the midterm, we will just use the class time. So the 1 hour and 15 minutes for the class, I will do that remotely. So I think my plan is that we will release the text problems to you at the beginning of the class, and you will submit your answers at the end of the class. So we can make sure everybody is doing this at the same time. And also you don't need to reserve extra time for taking the test. It's just the class time. That's the plan, yeah. Okay, and let me see any other questions from, okay, I think we covered everything, right, in the chat box. Okay, so that sounds good. And if you have any suggestions, or if you are a very, if you're very sure that you definitely want to do in person, please definitely let me know. So I want to hear people's voices. How about discussion? Okay, I think the discussion will go with the lecture. So whatever we do with the lecture, the discussion will be the same. So if the lectures are remote, then the discussion sections will be remote. Okay. Thank you. And I will make sure I post those points to the Cecilia's announcement. So you will have an email copy of this. Okay, so just to continue our lecture. Okay, so I think I received some feedbacks from students, also from the discussion sections, which I want to make sure that we have everybody on the same page. So the first thing I want to say is, I think I've said this enough, right? But I still want to emphasize the importance of mathematics for learning statistics. So this is why this class is called mathematical statistics. The adjective mathematical means that we're using math to study statistics. And here the foundation is probability. And probability is actually a discipline of mathematics. So if we talk about the history of probability, right? So you can think of probability as a specialization of a topic called measure theory. Actually, measure theory is a core course of mathematics major undergrad. So that's why I think a lot of things are coming from there. So you can see that from from measure theory to probability to statistics, things are going from abstract to concrete. So statistics is the concrete realization applications of probability. Let's put it this way. But even if you are going to do statistics, right, not talking about probability, you still need to use probability as a tool, as the mathematical tool. And even though you may not be a PhD in the future, you're not interested in doing a PhD, you just want to be a method user. But if you really want to know what's inside those R packages, R functions, math background is still very important. So what I would say is that I think learning math is always useful. So if you want to do it, then go for it. But I don't want to use math as a bottleneck for this data science practice. Honestly, I don't want to do that. So that's why I would say that in this class, I will try to give you more intuitions so that we can try to make those math definitions a little more concrete, less abstract. So that's why people can better understand it. So the intuition would be the first place to start with. Why do we need those things? Okay, so therefore, to quickly recap what we have done and also try to make up this background a little bit for our students who didn't learn continuous random variables or continuous distributions from 108 or any prerequisite. So I want to say that these are the concepts I hope everybody can really understand after this class. So basically, I want to say that these are the key things that people should know if you want to make up some of the background. So let me just grab this piece of paper. And okay, sorry, give me a second. Okay, so these are the key concepts I want everybody to know. I think there are a lot of good tutorials or even cartoon videos to explain those concepts. So the key concepts we will use throughout this class include random variables, right? This is the starting point. And associated with random variables are distributions, probability distributions. So these two things, random variables and their distributions, are hand in hand. So they cannot be separated. So when we say random variable, I mean the random variable can take more than one value, usually. Okay, can take different values, and these with different probabilities. So how do we describe the probabilities associated with different values is what we call probability distributions. So for discrete random variable, this is very obvious, like Bernoulli, 0 with probability P, 1 with probability 1 minus P. That's very straightforward. But for continuous random variables, it becomes trickier. So to fully understand that, you do need some background about measure theory, but I'm not going to touch it here. So for continuous random variable, the tricky thing is that because it can take so many values that are so densely connected, then its probability of taking one particular value is actually only 0. So you cannot talk about that probability, but you can talk about the probability that the random variable takes values in an interval, as long as the interval has a non-zero probability. Okay, so basically we talk about the probability of a continuous random variable in an interval. So motivated by that, to describe the probability distributions, we have introduced 3 concepts so far. Okay, so under this, we have what we call the probability mass function. Mass function, PMF. Okay, this is for PMF. This is for discrete random variable. We use this to describe it. For continuous random variable, we use probability density function, short as PDF. Okay, so these 2 things correspond to discrete and continuous random variables respectively. Okay, they are one thing. So this is about the probability or the density that my random variable takes a particular value. And then cumulatively, we have the CDF. Okay, CDF is applied to both discrete and continuous random variables, and it's defined as the left tail probability. So it's defined as the probability that a random variable x, big X, takes value less or equal than any particular value, small x. So CDF is a function of the small x. Okay, so that's why we write it as big F, small x, because it's evaluated at the small x. And finally, we have what we introduced in this class, MGF, moment generating function. So it can also specify a distribution. So what we learned for the most important thing about MGF is that if you want to show a random variable follows some distribution, then we can derive the random variable's MGF from the definition of the MGF. Okay, so the definition, we write this T, argument T is defined as expectation exponential to T times the random variable X. So if we can derive a random variable X MGF using this definition, and if we happen to know this form of the MGF is some distributions MGF that we know, then we can say, yeah, this random variable X follows that distribution. So in other words, MGF is a tool for us to prove whether some random variable follows some distribution. So it's a way to link to the distribution. So that's why I'm saying that so far what we have talked about belong to probability. So the thing is that we really want to understand the behavior of a random variable. And to describe that behavior, we can use the PDF for continuous random variable, PMF for discrete random variable. And regardless of being continuous or discrete, we can use the CDF and the MGF to describe the distribution. So these are the things we have taught so far. Okay, and one more thing I want to say is about the bivariate distribution, which some of you may think is more complicated. So when we say bivariate, we mean a pair of random variables. So in other words, if we denote one random variable by X, another random variable by Y, then we can say looking at them jointly is talking about their bivariate distribution. So I can give you 2 extreme examples to know why it's important to talk about them jointly instead of marginally. So let's say that I make it simple. Let's say X follows a uniform distribution between the interval 0 and 1, and Y also follows a uniform distribution in the interval 0 and 1. Okay, so now I'm going to draw this interval 0 to 1 for the 2 dimensions. This is for X, this is for Y. Okay, then I can tell you that when X and Y are independent, so I talk about, this is another concept that everybody should know, independence. Independence, intuitively, it means that whatever value Y takes has nothing to do with the distribution of X. So in this case, if X and Y are independent, which can be denoted by this perpendicular sign that can mean independence. So when this happens, it means that at whatever value of Y, my X will always follow this uniform 0 to 1 distribution. So in other words, I can write this as X given Y follows uniform 0 to 1. At any Y, the distribution of X is unaffected. So by uniform, you can see that, say that it's like X can take these values with equal chances, right? And at any value of Y, it's like that. And Y itself is taking uniform 0 to 1. So then you can imagine if I draw points from this space, right? X is between 0 and 1, Y is between 0 and 1. If I draw points from this space, then the points will uniformly scattered in this rectangle, right? That's what the distribution will look like. Does that make sense to everybody? That means when we do sampling, sample points from this distribution. Okay, and then I can tell you another extreme scenario. Still, X from 0 to 1, Y from 0 to 1. But I'm giving you this extreme case that X equals Y. So they are equal to each other. So whatever value X takes, Y must take the same value. Then if I want to draw distribution from this, what will it be? So you can see that in this case, if I do the distribution of X given Y, Y is given, then I know this distribution is just a point mass at Y. By point mass, I mean that X can take only one value with probability 1. And that's the case. Because X is said to be equal to Y, then when Y is being conditional, which means I know what value Y takes, then X must take that same value for sure. There's no other options. So therefore, if I'm going to sample points from this distribution, you can tell me what will the points be like? Yep. And linear, yep. Yeah, so they will lie in this diagonal line perfectly. So still X will be uniformly between 0 and 1, but whenever X takes that value, Y must take the same value. So that's why they will lie perfectly on the diagonal line. So this can tell you why we should talk about bivariate distribution, because in those two cases, if you look at X and Y separately, their distributions are both uniform 0 to 1, but the points are totally different. That's because in this case, X and Y are independent, and in this case, X is equal to Y. So that's why when we talk about bivariate random variable, we do care about how the two variables are dependent. Does that make sense? Okay, so then we talk about the joint MGF, if you recall. The joint MGF of two variables, which we have denoted as this, mxy, right? mxy as t. So by definition, if you recall, this is the expectation of exponential s times x plus t times y. So here, this expectation is about the joint distribution of x and y. So both need to be considered. And we give you a very important property about this. That says if, so I would say that this, if I define the marginals, right? So the marginal MGFs are mx at s, okay, equals to expectation as x myt expectation. Okay, So with those two definitions, one thing I want to say, in addition to what I'm going to say as the key result, is as a side note, I want to say that the argument symbol is not important. So I think I said this before, but I want to emphasize this again. So to see why this is not important, we need to understand that a function is a map. So what it does is that it maps from the value you enter here and outputs a value here. So basically, you can see that if I set s equals to 1, then I will get, maybe write it down. So you can see that if I set s equals to 0, then basically on the right-hand side, it will be this, right? And if I set s equal to 1, then on the right-hand side, the output values will change accordingly. So this is a map. Whatever values you input, you will get a value that's output. But whether you denote this value by s or by t, it doesn't matter. So that's why when we talk about a function, the key is to say mx is the MGF and my is the MGF. But whether calling the argument as s or t or r, it doesn't matter. Okay, so with this, given the joint MGF, given the marginal MGF, here's the important result that says using this MGF, we can talk about independence. So we say that x and y are independent. So in mathematics, we have a notation to say if and only if, right? So if and only if is basically equivalent to this double direction equivalence. So this is equivalent to that the joint MGF can be factorized as the product of the two marginal MGFs. So this is a result we are going to use next, I would say shortly, maybe at the end of this lecture or the beginning of next lecture. So using this result, we can easily show whether two random variables are independent. So to give you some preview, what we are going to show using this result is a very interesting result. That is a very interesting theorem. So let's say we have n random variables, x1 to xn, IID from a normal distribution with mean mu and sigma square variance. So then the conclusion we need to prove using this property is that if you recall, the average of the random variables we denote by xn bar, which is 1 over n sum of xi. This one would be independent. It's independent of xi minus xn bar for all I from 1 to n. So this is a very interesting result. We're saying that the average of those n random variables, IID normal random variables, is independent of the difference of each random variable minus the average. So intuitively, you wouldn't think them to be independent because both terms involve x and bar, right? So how would they be independent? But this is a special property about normal distribution. So I wouldn't say this hold in general, but for normal distribution, this is special. And that makes normal distribution so nice. And we will see that later. But to prove this result, we are going to rely on this property about the joint MGF. So hopefully, I think these can give you a better, I would say, justification about why we need to learn this MGF, this abstract concept. Okay, and of course, more importantly, the MGF can be regarded as a summary of a distribution because as we said in the first lecture, with this MGF, right, when you take its derivatives as 0, then those derivatives will correspond to the corresponding moments of the random variable x. So that's why, that's the name, moment generating function. Okay. All right, so that's all I want to say. And last time we have a very important result, right? One of the most important results of mathematical statistics from probability. This is called central limit theorem. So central limit theorem is very important because it has a magical result that the average of n IID random variables will behave like a normal random variable, normal distributed random variable, if n is large. So what we prove is that when we let n goes to infinity, that means we increase our number of IID random variables up to infinity, then the average, the distribution of the average or the sum after standardization. So recall that we can standardize the sum by subtracting the mean, state expectation, and dividing the square root of the variance. And we can do the same for the average. And what we said is that after standardization, these two ratios would be the same thing. They are equal to each other. And for this ratio, we can show that as n goes to infinity, the distribution of this ratio would approach standard normal. So in our last lecture, on Wednesday, we spent quite some efforts to prove this using the moment generating function. And if you recall, the idea is that we know the moment generating function of standard normal is just this exponential to the 1/2 t squared. So therefore, we want to show that the moment generating function of the left-hand side, after we take the log transformation, it will converge to this, right? So we spent quite some efforts to show that. That's the proof in our last lecture. But to help you understand what this really means, for today, I'm going to give you the R code I wrote to help you get some intuitive understanding of the central limit theorem result. So let me share my screen. Okay. So here it is. So basically, let me try to enlarge the text here. So what I try to do is that I sample n IID from a Poisson distribution, okay? And I set n equals to 3. So x1, x2, x3, each follows Poisson with lambda rate parameter equal to 1. So let's first take a look at what this looks like. So give me a second. Oops, I think okay. So basically, what I'm saying is that this command will give me 3 numbers. They are sampled from Poisson 1. So you see, 2 of them turns out to be 2, 1 turns out to be 1. So that's my x1, x2, x3. And then I take the average of them by taking the mean, okay? So in this case, you can see the mean will be how many? 5/3, right? That will be the mean. Okay, but what I'm doing is that I repeat this procedure for 1,000 times. The reason is that here the mean is only one value. So for that one value, I cannot talk about distribution, right? To see the distribution, I need to repeatedly do the sampling of x1, x2, x3. So see, if I do this again, now the numbers are changed. So this is the second time when I do the sampling, x1, x2, x3. So that means my x1 for the first realization takes value 2, second realization takes value 0, and third realization takes value 1. So then basically for each realization of x1, x2, x3, I compute the average. So that will be the average of my xn bar. So here my xn bar will have a realization here, 5/3, 5/3, and 1. So I do this for 1,000 times, and then we will get 1,000 realizations of x bar. And then let's look at the distribution by plotting a histogram. So you see, this is what it looks like. It's not like a normal distribution, right? It's not a normal distribution for sure. And if we compare it to the normal distribution using a QQ plot, you see, it's not good. Not a very straight line. Okay, so that's the thing. So of course, in this case, when n is equal to 3, then the central limit theorem doesn't hold very well. But now I'm going to repeat this by enlarging n to 500. So now the n is so much larger. And let's see whether now the distribution of the average is closer to a normal distribution. All right, I obtained the 1000 realizations of X and bar. And let's take a look. So now those 1000 realizations of X and bar does look like more normal, right? It has this normal shape. And if we look at the QQ distribution, now it's much better. It's close to a straight line. Okay, so the first example, my IID random variables are from a Poisson distribution, okay, with mean 1 and variance 1. And actually, looking at this histogram here, you can see what is the mean of this normal distribution for the sample average? It's actually at 1, right? Recall that we told you, we said that the average X and bar would have expectation equal to the expectation of each Xi. So it should be 1. And the variance of X and bar should be equal to the variance of each Xi divided by n, which is what? So the variance of Poisson 1 is actually Poisson is actually 1, right? Here we have n equals to 100. So basically, we would have the variance of X and bar at 500, sorry, as this. That will be the variance. And then looking at this normal distribution, we want to know what's its standard deviation. Standard deviation is the square root of the variance. So about 0.045. So therefore, what we can know is that from the normal distribution, if you know, 95% of the probability is within 2 sigma, 2 standard deviation from the mean, right? So 2 standard deviation here would be about 0.09. That's exactly what we see. So from here to here, this is about 2 standard deviation. From here to here, about 2 standard deviation. So roughly speaking, this histogram matches our theoretical result. Okay, so that's the first case. The IIDs are from Poisson. Now I change the problem to IID from exponential distribution. Still, I start from n equals 3. Sample also 3 random variables and look at the distribution of X and bar, right? Far away from normal, right? It's not normal at all. And if we look at the QQ plot, still very bad, right? Normal distribution, not really good. But now I increase n to 500 and see histogram. Right now we have this bell shape, okay, for those 1000 realization of X and bar. And now let's look at the QQ norm. Now pretty straight. So this is another case saying that we start from exponential distribution, not from Poisson, but as n gets to 500, the average will have a similar distribution, approximately normal. Okay, so finally, we want to look at this example. Now we have a binomial n, p. Okay, so binomial can be regarded as the sum of IID of n IID Bernoulli p. Okay, that's the definition of binomial. And actually get back to this very soon on my paper. But let's show the example on code first. So you can consider this as the sum of n IID Bernoulli p, binary random variables. And for the sum, let's take, so now we're looking at the sum instead of the average. Let's see whether the sum follows a normal distribution. So first I start with n equals to 3. So this n is this n, is the binomial n, while this 1000 means I'm going to sample 1000 times. So let's first take a look at the distribution. That's it. With n equals 3, the sum looks like, okay, 0, 1, 2, and 3. So, and it doesn't look like a normal distribution for sure, right? So QQ norm would show this. Now I increase the size n to, maybe to be consistent, maybe let's just change this to 500. So we have n equals 3 and n equals 500. So I'll delete this one. Okay, was this n much larger? Now you see the histogram of the sum looks more like a normal distribution. And also the QQ norm will tell us the same answer. So hopefully these will give you some intuitive understanding of the central limit theorem. That means no matter my IIDs are from Poisson, exponential, or Bernoulli here, I can always have the average behaving like a normal random variable. But of course, this is because in our discussion here, the distributions we picked, the Poisson, exponential, and the Bernoulli distributions all satisfy one important criteria. That is the condition we give in the central limit theorem. That is the second moment or the variance of the distribution is finite. That's the must. That's what we need to really have the central limit theorem hold. Okay, so based on what I just said about the central limit theorem, so actually in our lecture notes, the one actually I posted to the homepage, the combined lecture notes, we actually have this example. So I would say it's, so check the combined lecture notes. Check the combined lecture notes. Pages 13 to 14 on posted to Cicely. So in that place, actually we give this derivation. So y the binomial with n IID as the sum and p as the probability of success can be approximated by a normal distribution. And in this normal distribution, I'll just give you the answer. The mean would be the same mean. So it's n times p, which is the binomial mean. And the variance will be the binomial variance, np times 1 minus p. Can be approximated by this normal distribution when n is large. So in that place in the note, we will actually first use central limit theorem to say, yeah, this should hold. But if you don't want to use central limit theorem, you start with the moment generating function of binomial. You can also show that as n goes large, goes to infinity, the moment generating function of this binomial would converge to the moment generating function of a normal distribution. So what defines large n? That's a very good question. So I would say in practice, usually n above 20 can be considered quite large, or n above 50 can be considered quite large. So that's what people mean. So actually in this class, we will not talk about this convergence rate because that's a more advanced topic. But in my other class, actually you can find the videos online in my playlist, the Stat 203, when we talk about large sample theory, we specifically talk about the convergence rate of the central limit theorem, which is 1 over root n. So 1 over root n can be considered a pretty fast rate. That means that if n is 100, then 1 over root n is 0.1. So 0.1 is basically what you expect to be like the difference between the current distribution and also the normal distribution, something like that. So it's not accurate what I said, but basically 1 over root n is the convergence rate. So you can see that in statistics, right, the rate is very important because 1 over n is faster than 1 over root n. And 1 over root n is faster than, say, 1 over log n. So that's why people want to see this rate will determine or answer your question, how large n is large enough. So to really understand that, I think a lot of people will use simulation to play with different n and to see how well the distribution can be approximated by normal. And I can tell you that this also depends on what's the original distribution of the IID. If the IID random variables are from a symmetrical distribution, then the convergence will be faster than if they're from an asymmetrical distribution. So that's what I would say for this class, as just some intuitive understanding. Yeah, so the code was posted. So the previous code was posted, so I will post this code as well. But I'm not sure whether everybody here has some R program experience from previous classes, but I guess so, right, from the Stats 20. Okay, and there's another question. Does it mean, for example, in an experiment, if the number of replicates for each measurement is large enough, the average of the replicates must be like normal distribution? Yeah, roughly it says so. As long as the measurement is not following a heavy tail distribution without second moment, without finite second moment, because that's what the condition of the central limit theorem. But for most cases, you should not be worrying about that, right? The distribution shouldn't be too heavy tail. By heavy tail means that the measurement has a large chance to take extremely large values. That's what we mean. But this case can be seen in financial data, like stock market data. I know in those cases, people talk about distribution that may not have finite variance. And also, central limit theorem, this means that when we say behave like a normal distribution, we must have multiple, we were thinking about multiple realizations beyond what we see. So for example, in your data, in your experiment, you have, say, n measurements, you take an average, then that's just one realization of xn bar. You don't have other realizations, right? But what we're saying, this normal distribution, is that imagine if we have other potential realizations, then those realizations all together will form a normal distribution. Does that make sense? Okay, so we will actually see this later when we talk about the hypothesis testing and confidence intervals in the later part of this class. So I will leave this to you to read, right, about the convergence of binomial to normal. So now I'm going to give you a concrete example about the application of central limit theorem, and this is related to your homework. So in this example, let's say that we have a sample of 100 values from a population. Population is also used to as a, sometimes I would say most likely an equivalent to the distribution. So we use the distribution to describe a population. From a population with mean, let's denote this by mu 500. And let me say this n equals 100. Okay, 100 is the number of values, mean 500, and standard deviation sigma denoted by 80. Okay, so that's the setting. Then the question we want to ask is that what is the probability that the sample mean is in the interval 490 to 510. Okay, so that's the question we want to answer using the central limit theorem. So to know that, we must know, so here when we see the probability, the first question to ask is, what is the random variable we talk about? Here the random variable is the sample mean. We consider to be random, and we consider this interval to be fixed. So therefore, let's denote that as x1 to xn are IID, right? IID from a distribution with mu equals to 500 and sigma equals to 80. That's what we know. And we also know n equals 100. So therefore, to use the central limit theorem, to make it more explicit for people, basically the central limit theorem is telling us that for large n, here n equals 100 is considered pretty large, the xn bar would be approximately following a distribution with its own expectation and its own variance. So I will just write it here with its expectation, xn bar, and the variance, xn bar. So this is central limit theorem, what it tells us. So now what's left for us is to derive this expectation and variance. So note that the expectation of xn bar can be written out by definitions. I'm going to do the derivation once again for everybody. So it's this average. Okay, that's the definition. And now because of this importance property about expectation. So, okay, so coming back here, I should say for the key concept people must know, I will also make expectation and variance here. So these things will be used throughout this class. Okay, so here the expectation has that linear property. We can make expectation into the sum. So then it becomes 1 over n sum of expectation of xi. Okay, and because here they are IID with the same mean mu, so therefore you see it's just put it here 1 over n summation I from 1 to n of mu. So because it's the same mu that's added up for n times, then it's basically n copies of mu, and that n can be canceled with this 1 over m, so I'm left with mu. So that's why the sample mean has the same expectation as each xi. I think this is something people should be familiar with now. And then the variance of xn bar. Okay, so I'm going to use the definition of xn bar again. Okay, now because they're IID, right, independence. I got a question in the email saying that, okay, I said when we do the expansion, the variance, we should keep the covariance term of each pair of random variables. But that covariance, those covariance terms can go to 0, can be 0 when these xi's are IID because of independence. Then for each pair, say xi, xj, their covariance is always 0 by independence. So therefore, because of the independence, I drop the covariance terms, and this 1 over n goes out after squaring. So I would have 1 over n squared. Okay, goes out. And then I can put the variance into the sum. Okay, that's what I have. So moving to next line, 1 over n squared stays here. And inside the sum, because of the identical distribution, every xi has the same variance sigma squared. So therefore, it's the same sigma squared that's added up for n times, and that n can be canceled with 1 n in the denominator, and I'm left with 1 over n sigma squared. That's it. So that's why here the variance of sample mean is the variance of each random variable divided by m. So coming back here, this distribution is actually mu sigma squared over n. That's the distribution we can use for normal. That's the normal distribution we can use to approximate the distribution of the xn bar by central limit theorem, short as CLT. Okay, we are going to use this to compute the probability that xn bar is in this interval. Okay, so basically the answer can be written as the probability that my xn bar is greater than 490, less than 510. That's the probability we would compute. Okay, and now to compute this, we are going to use this distribution we know for xn bar. Actually, these two numbers are known already. So based on the setting we gave, mu is 500, sigma is 80. So we will have 80 squared, okay? over n. N is 100. So that's the distribution of x and bar. We know it. And so to compute this value, we are going to use what we know from standard normal distribution, because the standard normal distribution is whatever is available as a table in some textbook or in R, right? So we could actually do it. So basically, what we can do is that we can standardize this random variable xn to make it standard normal. Okay, so let me just quickly go here. So from here, we can say that xn bar, if we standardize it by subtracting the mean, okay, 500 divided by its standard deviation. So the standard deviation will be the square root of this. So that will actually be 80 over root of 100. And we know that root is 10, right? So basically, it's 80 divided by 10. So it will be xn bar minus 500 divided by 8. That's the standardized version of my sample mean. And by the central limit theorem, this will follow approximately standard normal. Okay, does this make sense to everybody? Is everybody following? Great. Okay, now coming back to this answer, right? I'm going to make this as a probability with the random variable as the standardized one. So I can use the standard normal distribution. All right, so then going down here, I will standardize the middle. So xn bar minus 500 divided by 8. And I will do the same standardization for the left boundary and the right boundary. So it will be 490 minus 500 divided by 8. In here, it will be 510 minus 500 divided by 8. Okay, so finally, the left-hand side can be simplified as negative 10 over 8. So that will be negative 5 over 4. That would be negative 1.25. Okay. So on the right-hand side, it will be the positive 1.25. So therefore, this probability, if we know this normal distribution, standard normal distribution, let's see, this is standard normal, okay? So which is centered at 0 with standard deviation 1. Then this answer is basically asking us the probability from negative 1.25 to positive 1.25. And what's in the middle? So this area would be the answer. Okay, so with this knowledge about the standard normal distribution, this is the area I want to compute. So now let me give you this actual number. We can actually go back to our R code. So now with R, we don't need to look up the table anymore. We could just do it in R. So going to R here, basically this would be simply, R has this nice function called the P norm. So P norm means that if I input the value 1.25, it will actually give me the CDF function 1.25. So basically, it's the probability that a normal random variable I call Z is less or equal than 1.25. That's what this function will give me. Okay, but this is just for your information, but R will not recognize this. I'll delete this. So that's the left tail to the left of 1.25. And also, I want to subtract the left tail of negative 1.25. So that's the two left tail probabilities. And my answer will be the difference of those two. So basically, if I do this minus this, okay, this will exactly be the probability that a random variable, standard normal random variable Z is between these two values. That's exactly the probability I want. Okay, so I will delete this and give you the answer. So here, the answer will be 7.7887. So that's the answer we will have for this problem. Okay, so let's come back to paper. So with this, then we use R to do the calculation. It's 0.7887. Okay, so I understand that probably for some of you, using numbers as examples probably make it more intuitive, right? So the answer becomes more straightforward. But please note that we don't need to give you actual numbers. So I can change this interval to any A to B interval, just telling you A represents a constant, B is a constant, and A is less than B. So with just abstract A to B interval, all the calculation will still carry over, right? So in the abstract way. So what I'm trying to say is, let me get a different piece of paper. So what I'm trying to say is that if I change the problem to be just this abstract problem and IID with mean, mu, and standard deviation sigma, same setting. And what's the probability? I'm interested in asking you, what's the probability that my XM bar is between A and B? Just an abstract interval without numbers. So to do this calculation, when n is large, don't forget this. So to do this calculation, we will still follow the same idea. That is, we would have XM bar follows approximately normal distribution with mean mu, variance sigma square over n. So I'm giving you the result I just derived. So therefore, this will tell me XM bar minus mu standardization over sigma over root n would be approximately standard normal, right? So then finally, to compute this probability, I'm going to rely on the standard normal. So that is for this probability is equal to, if I standardize every term, A minus mu over sigma over root n, B minus mu over sigma over root n will be this probability. Now I'm going to use the fact that XM, oh, sorry, I forgot the standardization, my bad. Okay. Now I'm going to use the fact that of this. I'm going to use this approximate standard normal distribution. So therefore, I can write this probability by the CDF function of standard normal. So this will be equal to the CDF function evaluated here minus the CDF function evaluated at here. Okay, that's what we have. So where this is the CDF of standard normal, which means that if I evaluate the CDF at any value x, it's defined as the probability of z less or equal than x, where this z is standard normal. That's what I mean. So essentially, based on the R code I just showed you, this thing in R is basically that that P norm function, the P norm function I just used. Okay. So I'm saying that we can answer this question in general using this way. And in your homework, you're actually going to show something related to this formula. So that's why I want to give you this hint here. So you can talk about how the CDF changes as the argument enlarges or decreases. And a note is that the CDF function is monotone increasing. Okay. So therefore, using this, you can see I can plug in any numbers, A and B, mu and sigma and n, to make this into a number. Okay, any questions about this application of the central limit theorem? Okay, so if not, then I will move on. But there's another further sub problem besides this one, but I think it's very similar. So I'm going to skip it, but please read it yourself. So basically that's at the end of page 14. So that's what I said. So try to read pages 13 to 14 in the combined lecture notes. It covers some more details which I didn't talk today. Okay, so I will move on to our next topic, which is something I find very interesting. It's called the chi-square distribution. So we use this a lot in mathematical statistics. But to talk about the chi-square distribution, we will actually start from its general form, gamma distribution, which is something you have already used in your homework. So gamma distribution is a general type of distribution that describes random variables that takes real positive values. So the positive part of the real line. So let's say that we call a random variable x follows a gamma distribution with 2 parameters. Gamma must be specified with 2 parameters, just like normal distribution also must be specified with 2 parameters, mu and sigma squared. Here we call the 2 parameters alpha and beta. So for this, and this is a continuous distribution, okay? So this is a continuous distribution, and also this x only takes non-negative values. And alpha and beta, the 2 parameters must be positive. Those are all the requirements of a gamma distribution. So looking at the gamma distribution, how about its probability density function, PDF function? We write this density function as the small f, and this function takes value at x in this form. So its density is that at this x is that x to the power of the first parameter minus 1, alpha minus 1, multiplied by an exponential function of x, negative x divided by beta. So you see my argument, the value random variable takes, small x, appears in the polynomial power function, appears in the power function and the exponential function. And the denominator is just what we call normalization constant to make sure this density integrates to 1. And that's beta to the power of alpha times, this is a function called gamma function, which I will talk shortly, gamma function at alpha. Okay, this is the density function. So by the nature of a density function, we know on this domain of x, right, x takes value from 0 to positive infinity. If I do the integration of the density function, it must be equal to 1. That's the definition of a density function. And then because of this definition, you see what it means is that I put in the form of the density function x to the power alpha minus 1 exponential to negative x over beta, beta power alpha, gamma alpha dx. Okay, that's what I have. And then what I do is that I can move the constant out of the integration. So this actually gives me the definition of the gamma function. You can see that this will tell me gamma alpha for a positive alpha is actually equal to the integration of x to this power that's it. So because that the density integrates 1, this immediately tells me, this must be the form that gamma alpha should take. And this is the definition of a gamma function. So gamma function is defined as an integration. And this is the integration that defines gamma. So basically you can see gamma appears in 2 places. One is in this power here, and one is in here. And actually, you can see very interestingly, this one actually doesn't depend on the beta. So beta can be anything, and when we do the integration, this would hold. Okay, so that's the definition of gamma function. You can just consider to be a complex integral, but we simplify this to be called as gamma function. And it has nothing to do with the random variable value. The random variable value is just a small x. That's the value that can change, right? We put it here in the power function, and also we put it in the exponential function. So that's the gamma function. And we can actually say that the first alpha parameter, it will determine. So actually, maybe I should give you this as a better explanation. So just give me 1 second. Yep. So I'm showing you the Wikipedia page so people can take a look together. So in this Wikipedia page, you can see that its two parameters are called differently. They're called as K and theta, while I use alpha and beta, but they have that one-to-one matching relationship. So basically, yeah, this is the one I use, right? So, oh, no, this is the one I use basically. So you see that the first parameter is in the power of x minus 1. Right? And the second parameter is in this denominator of the exponential function. So basically the notation I'm using, I call this alpha, I call K as alpha, I call theta as beta. That's what I'm using. But there's an alternative definition you can see here. That means here, this first parameter is basically the same. It's still the power of x, right? But the second parameter is now the inverse of the second parameter here. So you see here, the theta is in the denominator of exponential function, while here beta is just multiplied to x. So basically the beta is equal to 1 over theta here. So these two, you can see these two parameterizations in the literature, in other papers. Some people use this, some people use that, but it doesn't matter, they're equivalent. The only thing is that the first parameter is always called the shape parameter, but the second parameter is called the scale if it's in the denominator, or the rate if it's the inverse. So we use this parameterization, and let's take a look at the corresponding density. This is the density. So I'm saying that the random variable x, gamma random variable, takes only non-negative values. And you can see that's the case. And it can take values with different probability densities with different parameters. So for example, one trend we can see here is that if we increase the shape, the first parameter from 1 to 7.5, the mean is actually shifting to the right. The random variable is taking larger and larger values, right, with larger probabilities. And the scale parameter is actually playing what role? So let's take a look at this one. So from this, let me see if we have a good example here. Not a very good example to demonstrate the effect of the shape parameter, sorry. But anyway, so the mean here is their product. So as you can see that the larger the theta, the larger the mean, the larger the k, the larger the mean. And variance also has this formula. Okay, so with this gamma distribution, it's so because it has two parameters, it can be very flexible. By changing the two parameters, then the density function can take different shapes that may fit to your data. So you can see that unlike the normal distribution, which must be symmetric, the gamma distribution is not symmetric. Okay, so let's go back to our class. So here, the reason we want to introduce the gamma distribution is because of its generality. And we also know that there are special cases of the gamma distribution that are important. So let's say that, look at the special cases. In the first case, using our parameterization, let's set alpha equals to 1, beta equals to 1 over some positive lambda. Okay, so then let's see what happens to the density. The density function, you see when alpha becomes 1, this 1 minus 1 give me 0. sorry, yeah, and then x to the 0 is 1. So we will just remove the first term. And beta is 1 over lambda, so I will get exponential to the negative lambda x. Okay, in the denominator, it will be 1 over lambda to the power 1 times gamma function at 1. Actually, if you look at the definition of the gamma function at 1, it will actually give me 1, actually. Yeah, that will actually be 1. So I'm not going to say that here, but actually we can say we can show gamma 1 is equal to 1. So therefore, this can be simplified as lambda 2 times e to the negative lambda x. And this is what we call exponential distribution. So exponential distribution, which we have seen just in my R code, is a special case of a gamma distribution. Does gamma also become normal distribution if n is large? Actually, yes. But here you need to say what is n. So you mean if I have IID from gamma, and then I take the average of my IID, then that average will follow the central limit theorem and converge to normal distribution. If that's what you're asking, then the answer is yes. So gamma distribution also satisfies that it has finite variance, so the central limit theorem applies. Yep, that's the first special case. And now let's look at the second special case. Now we set alpha equals to 1/2 and beta equals to 2. So then here the density becomes the numerator is x to the power 1/2 minus 1, negative 1/2, exponential to negative x over 2. Okay, in the denominator, it will actually be 2 to the power 1/2. So that will be this. And finally, we have gamma function at 1/2. Okay, and for this density, we give it a definition. We call it chi-square distribution with 1 degree of freedom. So this subscript means the so-called degrees of freedom, which is the only parameter that the chi-square distribution needs. So that's why we define that here we define this as the chi-square 1 distribution, which is also a special case of gamma distribution. So we just want to say that gamma distribution is a broader class of distributions that includes exponential and chi-square 1 as its special cases. Okay, then why do we want to talk about this chi-square 1 distribution? The reason is that it's a very nice distribution to be used. You can consider this to be the squared version of standard normal. Okay, that's the thing we want to talk about. We call this a theorem. So when we call it a theorem, it means that it's really important. Let's say it's theorem 1. So let's say that we have a random variable z that follows standard normal distribution. Okay, then we can say that z squared. You see, standard normal random variable can take values positive or negative with equal chances, right? But when we square it, it can only be non-negative. And then the square random variable would follow chi-square 1 distribution. So that's why I'm saying chi-square 1 can be considered the squared version of standard normal. And in other words, we just derive the distribution of z squared and show that it happens to be in this form and it belongs to the gamma distribution family. Okay, so this is something I'm going to quickly wrap up today, but I think maybe we can just give you the beginning of this proof. So the beginning of the idea to prove this is to use CDF. So we want to derive the CDF of z squared and go from the CDF to the PDF and show the PDF is this form. Okay, so the idea is to go from the CDF of z squared, which is defined as the probability that z squared is less or equal than any value small x. And then we will go from this CDF of z squared to the PDF of z squared, denoted by fx. Okay. And here, maybe I should give this CDF a notation. Let's call this big fx. Then the PDF fx is known to be the derivative of the CDF. And then finally, show that the CDF fx happens to be this form. So that's the whole idea of this proof we are going to do at the beginning of next time. But you are very encouraged to try it yourself. Okay, so it's basically some algebra here. The idea is very clear. So to actually derive the CDF of this, we are going to use the fact that z itself follows standard normal. So we'll go from there. All right, so I will stop here and I will see you on Wednesday. Bye.
Hi, I have a question on problem 3 of the homework. So should you suppose that for part 2 of problem 3, should you suppose that x follows the exponential distribution just like part 1, or?
So you are talking about problem, which problem?
Problem 3, part 2.
We are going to use the central limit theorem, but in order to derive the expectation and the variance of the sum, you are going to use part 1. Yes.
Okay, so we're supposing that x follows the exponential distribution and the sum of x, Sn follows gamma distribution, right?
Yes, you can do that. You can use that. Yeah.
Okay, thank you.
Thank you.